Okay, that's, I think, better now. There's a couple of people watching in YouTube and they didn't say anything. Nice. Anyway, um, if someone watches the live video, this part won't work. I have to re-record it. You're here live, so it doesn't matter. Okay. Number 3, just so we have a video backup that works. Formula is a 1 equals 2, excuse me, then they give me a n equals 3a n minus 1. Well, they can't really hide the recursive formula and the fact that it's a geometric sequence. I can see it right away, right? But if you don't, perhaps, that's okay. We can just make the sequence. This says start with a 2 and multiply the previous one by 3 to get the next one. Next one. What's 18 times 3? So clearly, by the instruction of the recursive formula, it is a geometric sequence. There's not much to hide here. It is a geometric sequence, I say, with first term 2 and ratio e. Now, what they gave me was a recursive formula. I need to write down the explicit formula, the other kind of formula. But I have it memorized, so it's not a problem. First term times ratio to the n minus 1. And it works for all. This n minus 1 is an n minus 1 for very much the same reason as there was an n minus 1 in my arithmetic sequence formula as well, right? And I remember it just as it comes out of my table, out of my discovery. There is no need to simplify this or modify it in any way, just like I didn't modify the arithmetic sequence formula. Could, but I have no need. I like to see the pieces and where they go. Right, so I think so far it's good news in that multiplying by the same number every time is really not a big deal. Now I'm just going to skip ahead for a little bit and do exercise 3.5 because geometric formulas have a very, how should I say it, frequently used application when it comes to finance and interest rates and things like that. Let's explore this briefly just to see, okay, these things aren't just made up to keep you busy. They are literally used every single day. So exercise 3.5, I shouldn't have taken it away that fast. Suppose I have $2,000. Let's just say at the end of 1 year, year 1, I have $2,000. The bank is very generous. It's going to give me 5% interest and compound that annually, meaning at the end of the year, it's going to add the interest to my account. And then the next year, I get 5% again, but on top of my new amount. No money's taken out or anything. I want to know 10 years down the line, how much do I have? Year 10. A pretty practical question. So let's just see what is the sequence. So now I'm just going to make these a little bit bigger. This is now going to be year 1, year 2, year 3, year 4. Now I want to see the detail in how I calculate the amounts of money I have as the years go on, but the first one just starts with 2000 because I want to identify it and explain why it's a geometric sequence. Now, when I, let's say here, increase 1000 by 5%. The calculation to do that, in case you've done 142, in case you've seen it before, in case you haven't, I don't know. My base 2000 is still there. I add the decimal version of the percentage and I multiply that by the number. And I realize that I have no space. That's okay. That's the detailed calculation in position 2. So after 2 years, no, not 2 years. Yeah, 2 years. Let's just see what that is actually. In MathBot, 1.05 times 2000. That is 2100. Now that 2100 sits for a year and gets 5%. So here I'm going to increase 2100 by 5% and get 1.05 times 2100. And I get, let's see what we get here. 0.05 times 2000. No. And I get 2205. Let's do one more. Then I'm increasing the 2205 by 5%. That's compound interest, right? Interest on top of interest. The calculation would be 1.05 times 2205. And our last answer, let's see what it is. 0.05 times 2205. And we end up with, after 4 years, 2315.25. Now, of course, we can just continue this systematically and hope we get to 10 years before we don't get too frustrated, but that's not very efficient. Instead, let me just redo this. First one was 2000. Then it's 2000 times 1.05. Doesn't matter which way I write it. Then I multiply that answer. This whole bracket is 2100. I multiply that by another 1.05. So I have two 1.05s multiplied to the 2000. 1.0. That whole answer, this whole answer, is the 2205, and that gets multiplied by another 1.05. So in total, I have three of them. 2000 times 3 1.05s, and so on. So you see, it's a geometric sequence. Geometric sequence with first term 2000 and ratio 5. And therefore, because I've now identified it as a geometric sequence, I know the formulas. In this case, I want the explicit formula because I want to jump ahead to position 10. First term, ratio to the n minus 1. So I can immediately use that to jump to year 10, which would be a 10,000 times 1.05 to the 10 minus 1. Let's see what MathBot says. 2000 times 1.05 to the power of, I'll just say 9. MathBot says 3,102 cents. 66, we can round it. So behind all those compound interest calculations that banks do and many people do sit these geometric sequences. Interest on top of interest. It's all multiplicative. And all those calculations, complicated as they may be in practice, they're all built on geometric sequence formulas. All right. That is all the good news that I have. But we just need to discuss why I say that. If we look back at the arithmetic sequence questions, we did exactly the same thing. Let's go all the way back, far back, past generalized. We had questions like these, like how many terms are there in this sequence, this arithmetic sequence? And given some information about an arithmetic sequence, can I find some other term and the formula and the whole sequence? Can't we do, or shouldn't we do these questions for our new sequence as well? Yes, yes we should, or at least explore what they look like. Now, of course, the geometric sequence grows much faster for a ratio larger than 1. Well, in either direction, it just grows faster. It changes faster. But I have a similar question here in 3.3. How many terms are there in this sequence? And I clearly see this is a geometric sequence, right? I multiply by 5 every time. Screen, it's a little small, but this is a geometric sequence, no doubt. So my goal here isn't to freak out anyone, which you'll shortly see that things just aren't quite as simple as soon as I step away from my very nice arithmetic sequence. Change that concept to multiplication instead of addition. And very quickly it grows to something very big here. One position. This is position 1, this is position 2, 3, 4. I want to find out how deep into the sequence is that. But to start with, I am going to identify it as a geometric sequence with first term 1 and ratio, also a very nice number, 5. So I set it up in a familiar way. I understand the sequence, therefore I have all the formulas. Great. Now, if you remember, and I of course assume that you remember everything there, for the arithmetic sequence, this kind of question, we use the explicit formula, right? The recursive formula is just a nice little introduction to start things off and translate into this language. Past that, it's quite useless, actually. But our explicit formula, we know. I've memorized it. First term is a 1 times 5 to the n minus 1. N equals 1, 2, 3, and so on. Now, I can simplify it to make my life a little bit easier. Because this is a 1, I don't have to write the 1. 1 times anything is just that thing. But if I have a different first term, of course, that changes the game. So here is my explicit formula. What did we do in the similar case, but the arithmetic sequence formula? Then all we said here was, let's call this position n. And in this, we'll call an. Some term, I want to find its position. So now let's set an equal to this 97. I need some commas here. This is way too much. 9,765,625 in my formula. That's what we did last time, right? Same thing, doing the same thing. It's just a different formula because it's a different sequence. So now we have to solve this equation. X to 5 equals 5 to the power of n minus 1. That's our equation we have to solve. Now let's compare that with a similar situation for the arithmetic sequence. Let's do it over here like this. Compare with what the arithmetic sequence or the arithmetic problem like. The arithmetic sequence, similar problem, had something like, I don't know, 1 plus n minus 1 times 5 equals blah. I don't know what the number is. Something deeper in the sequence. I'd have to make the sequence to make sure that number actually occurs. However, something like this is what we had to solve. And with our basic variables and equation knowledge, we could do that. The unknown n is in what I call the base level. Everything is in the same level. However, that's not what happens now, unfortunately. Here, the unknown, which is n, is in the exponent level. And this is an exponential equation, which isn't solved in the same way as the equation I've seen before. So now we have two choices. So very quickly, the problems are the same, but for a different sequence, the resulting equation that I have to work with can be much more complicated, and I might not have the background to handle things. But again, it's worth seeing. I have two choices. Here's my equation. Equation doesn't change. First choice is guess and check. Luckily, we know that the value of n is the position that this term is in. We can just try some positions until we hit the one we're looking for. That's not that bad. Guess and check. Now I don't want to think, oh, this is position 3. No, of course it's not position 3, right? If I look at my sequence, it's hard to guess, but let's maybe try position 10, which might not be right, but I'm just guessing. I don't know what the answer is. So here's my guesses. My position and the term in that position. My first guess, position 10. I'm not trying to look for a pattern here. I'm just making a table for convenience. Now, how do I calculate that? It's 5 to the n minus 1, right? 5 times 5 to the power of the position minus 1. So we'll let MathBot do that. 5 to the power of 9. So I don't know my powers of 5 that high. Remember, it's the position minus 1. I get 1,093,125. And I see, ooh, I'm a little short. I am close, though. I'm 9 million. This is close. I think it's just the next one. So let's try position 11. Put it in MathBot. Remember, it's 5 to the power of n minus 1. Position minus 1. So it's 5 to the power of 10. 5 to the power of 10. I know my powers of 5. I don't know what my powers of 5 are that high, but we see this is exactly the right one. Well, it better be. It is. So we see have our winner. So that means the position that this term occurs in is position 11. So I can then say the sequence has 11. And you know, I was going back and forth the whole yesterday and this morning and last night. What level of detail should we show here? Because look how quick this guess and check was. Really not bad. It was manageable. I almost don't want to do choice 2. However, I will because I already wrote choice 2. What apparently I can't do is speak properly. But you see, choice 1 is going to be totally fine. If guessing and checking is all you can do here, it didn't take long. So feel free to ignore this completely. But I already wrote it down, so we're down the rabbit hole. Why not just do it? It's in the book as well. There is a way to solve something like this. A to the x equals some number c. A and c are some numbers, and x is my unknown. With a little pre-calculus, we can we call it a logarithm. X is the logarithm base a of c. And again, feel free to tune out if you're happy with guess and check. And this has an effective calculator function called the natural logarithm that I make in the form of a fraction, because if you look at your scientific calculator, this ln button is there. So if I have something like this, the solution is this. You see the a occurs there, the c occurs there. So for example, if I need to solve something very simple, 2 to the power of what equals 8? I know it's 3, right? But let's suppose we didn't. Way I would calculate that is natural log of 8 over natural log of 2. Let's try that in MathBot and see that it actually does give me the number 3. Natural log of 8 divided by natural log of 2. I know this looks scary, perhaps. It's the 3 that we know it should be. Okay. Now, this is used a lot in calculus. I know we're not doing calculus. Guess and check. Go to your happy place. It's totally fine. So now we want to solve 5 to the power of n minus 1 equals 9765625. This is now the unknown in the exponent level. N minus 1, natural log of 9765625 over natural log of 5. And then, of course, we have to add 1 on both sides to get the value of n. Let's see what MathBot says, and if they do get the correct value. Natural log 9765625 divided by natural log of 5. So over here we get this is 10, and of course that was the value of n minus 1, so we have to add 1 to get 11 again. Now, I don't know how you feel about this. Guess and check isn't always going to be this efficient in general when we have to solve exponential equations, because they're part of something bigger where the answer doesn't have to be a whole number. Then guess and check will never ever work. We exploit the fact that we're looking for a position. That position will be a positive integer. And there aren't that many we can try. We're going to stumble on to the answer without a lot of effort because of our specific problem. Not that big a deal to guess and check. There's nothing in this setting that you can't guess and check your way to. But because it's technically an exponential equation, it is unfortunately solved with that scary looking logarithm. That's the way it's done. There's more stuff in the book there. So now if we have the last question, similar to the arithmetic sequence question, I want to find out what sequence has 7th term this, 11th term that, and then use a formula to do whatever. Just make this smaller. This is our last exercise, exercise 3.4. So we have our sequence. We start with the first term. Don't know what it is. I'm going to call it A. And then we're going to start, our next one is going to be A times R. First term, ratio. Eventually, we're going to hit the 7th term. And it is 16,384. Remember, they get big very fast. Then we have 8, 9, 10, and 11 is going to be in 194,304. Same thing. I need to look at the numbers I have first. So I'm going to multiply by R, then multiply again, then multiply again, then multiply again. That's 4 times. So if I take 16,384 and I multiply R 4 times, so R to the power of 4, right? Then I'll get 194,304. Now this is even a different calculation, but at least my R is in the base level, so that's a win. So R to the power of 4, I can divide both sides by the 16,000 something. See how I just step away. It's the same kind of pattern, except I multiply instead of add, and suddenly things look so much worse. Figure out if R to the power of 4 is this, then R is 4th root of the right-hand side, like that. And let's see what R is. Now I have to remember my function in MathBot, so let me just try and remember here. Just test it on something small. Okay, the cube root of 8 is 2, so that works. So let's try it on this. Sixteen, 3, 8. 4th root. Like that. Oh, yeah, sure. 4. So now I know I multiply by 4 every time. The ratio is 4. Now I have to go from the first term and see, well, this is the first one. This is the second position. I multiply by R to get to the second position. I've multiplied by 2 R's to get to the third position. It's always one less. I multiply by 6 R's eventually to get to the 7th position. This was first, and this is next. To take R, I have to multiply by 6 R's to get to the 7th position. But I know what R is. R is 4. So 8 times 4 to the power of 6 is 16,384. So A is 16,384 divided by 4 to the power of 6. Let's see what that is. I don't know. 16,384 divided by 4 to the 6. It's also 4? Wow. That's nice. So, the geometric sequence, they're all the same, has first term 4 and ratio 4. So I have my formula that I can use to find anything I want. Oops. If I want to find the 20th term, A20, I simply plug it into my formula and I get what I get, and I don't get upset. Holy smokes, that's a lot. See, this thing just blows up. Anyway, there it is. So this is why we stop here. Next chapter is different. We have our arithmetic sequence. We can get on top of it. It's not bad. But as soon as we build in either direction, we build on top by adding numbers that aren't always the same, triangular numbers, and the formulas just aren't as simple anymore. That direction is interesting to see, but let's pull back. Or we take the kind of pattern but change the arithmetic to multiplication. That gets a little bit unpleasant as well very quickly. We look in that direction, know it's out there, come back to our happy place where we can handle things and get an idea of how the formulas are used and the language issue without getting overwhelmed, I hope. But it is important. It has value to sort of peek in the directions of complexity, to know it's out there, and to not think, oh, this is as easy as the whole topic is. No, the topic is stated. Reduction, but unfortunately not uh, wander off too far from that introduction. Any questions on this? Let's have a look at some problems. Why not? I think they're all good. Yeah, they're all good in the order that they are presented. All are very similar to exercises, so master the exercises first before worrying about the problem. Also note, tomorrow is, I don't have the schedule up. Where should this be? I can just show you the schedule now. See, tomorrow you have the task of watching the video on Fibonacci sequences by yourself, self-paced, self-paced. And then, of course, we have 2 Q&A sessions, so you're welcome to ask questions from that. The Fibonacci sequence is something very important to know about, but we're handling it differently from arithmetic and geometric sequences. We're not really doing a lot of calculations. It's too complicated. It's formulas. But in terms of how often it appears and how we're connected to it, it's definitely so a lot of oral test questions can come from this one, not a lot of calculation questions. And as you work your way through the video that I'll put in the playlist, I haven't yet, I'm going to do it soon, tomorrow or sometime this week, there could be a Fibonacci question in the quiz. But once you've worked through it, in the upcoming Q&A sessions, we can talk about what would a test question look like, what are the key things that you should know, and so on. We'll work through the video first. Not a lot of calculation stuff, just more knowledge things, I guess. You'll see what I mean. Any last words on this? I think we took this as far as we can without it being complicated. It's already maybe a little bit complicated. Do the guess and check. Guess and check is okay in this case. No thoughts. See you. I won't see you guys tomorrow. Maybe I'll see you in a Q&A session. Otherwise, maybe next week. Who knows? Use the time as you need to. All right. Until